Okay, yeah, thanks for that. Alrighty, so yeah, I'm Jonathan, and I want to talk about time series forecasting with deep learning. So this work is all based off my honours project. So yeah, if you want more information, you can hurry up my thesis once it becomes available. But yeah, this is a pretty in-depth summary of what I was working on. So a bit of a breakdown on the talk. So I'll start with just introducing what I mean by doing machine learning for time series. Okay, so from there we'll learn how to incorporate neural networks into our machine learning models for doing time series forecasting, and then we'll talk about an extension to a simple neural network model that I'll talk about. So we'll be incorporating flexible distributions to be able to handle more types of time series data. Then talking about ensembles, where we're able to combine many different models for time series data into one to get a better quality forecast. And lastly, a little bit of a section on Bayesian optimization for model selection. Okay. So that's, okay, so time series data, it pops up all the time. So in places such as finance, natural resource management, health and tourism. So yeah, we've got some examples of time series data. On the left, we've got the new daily confirmed cases of COVID-19 measured over time. On the right, we've got the value of cryptocurrency Bitcoin measured in US dollars. Okay, so yeah, just two examples of some time series data sets. All right, so now machine learning. So the way I think about machine learning is that the goal is to accurately predict some future quantity of interest given some observed training data. And machine learning can be sort of broadly broken up into two main types of learning. So supervised learning and unsupervised learning. There are some other types of machine learning that have become of interest in recent years, things like active learning, self-supervised learning, but I think the main two types of machine learning are supervised and unsupervised. So in supervised learning, the goal is to learn the functional relationship between explanatory and response variables. And we do this learning on the basis of some observed training data. As opposed to unsupervised learning, where the goal is to just learn the structure of the unknown sort of data generating process or data generating distribution. And of course, we do this learning on the basis of some observed training data. Okay. So in a time series setting, let's suppose that our time series data is going to be given to us in this form here. It's just going to be a bunch of observations, y measured over time. Okay, so we've got y1 to yn. We'll put that into a collection. We'll call that tau, and tau is going to be our training data. Okay, and we're going to view this training data as being the outcome of some random training data. So we've got this capital script T here, supposed to look like a capital tau. And these are just going to be random variables. So we've got capital Y1 to capital YN. Okay, so our data comes to us in this form when we're looking at time series data. How can we fit the analysis and forecasting of time series data into a machine learning framework? All right, so if we tried to use a supervised learning approach for time series data, then I mean, one thing we could do is we could treat the explanatory variable as being the time index t, and the response variable as being the measurement at that time t, right? So, I mean, you know, based on these plots, we could have an input as being the time and the output being the observation at that time, and we could try and learn sort of the functional relationship between input and output. So, you know, supervised learning could be suitable. What about unsupervised learning? Well, in unsupervised learning, the goal is to learn the data generating process, just learn about it. So in particular, what we would do is we would try to approximate the true data generating joint PDF F with some approximating joint PDF G, and G will depend on some model parameters collected into the vector theta. Okay, so theoretically, we could sort of try either way, supervised or unsupervised learning for time series data. But there's one key thing that will sort of shift us towards unsupervised learning over supervised. And that's because with time series data, we often have this strong serial dependence in the data. So what that means is that the current observation at the current time is going to depend quite strongly on the previous observations in the time series. So, for example, in population data, if you're measuring population over time, then if the current population is really large, then we would expect, at least in the near future, that the population would remain large. So the time series data has got a lot of dependence in it. And in supervised learning, a lot of supervised learning models have this implicit or sometimes more explicit assumption that the data is going to be independent. So the data we have is going to be independent, and the models that we use in supervised learning are typically going to assume independence. Not very suitable for time series data. So that makes unsupervised learning really nice and really natural for time series data, because time series data is usually not going to be independent. We can capture these dependency structures quite easily with unsupervised learning. Okay, so going down the unsupervised learning route, we can capture dependencies in our data. Now, remember, the goal is to approximate the true data generating joint PDF F. We do that with our approximating density G. One way of measuring how good our approximation is by using the KL divergence, Kullback-Leibler divergence. So the KL divergence looks like this. It's an expectation of the log of the ratio of the true joint PDF over the approximating PDF. Right, and we've just got a random training set plugged into these and taking the expectation with respect to the data. So if you've had a bit of experience with probability and statistics, hopefully you're comfortable with looking at formulas like this. And essentially the goal is to minimize the KL divergence, and that'll minimize the difference between our two distributions, right? What we're trying to approximate with and the true density. So we want the KL divergence to be small. Unfortunately, we can't actually compute the KL divergence analytically, because we never know what this true data generating PDF actually is, right? The whole goal is to approximate it because we don't know what it is. So we can't compute the KL divergence, but fortunately, if we're trying to minimize the KL divergence, the minimizer is actually the same as the minimizer of the cross entropy risk. Okay, so we can get rid of this F from the formula, and we're just left with an expression involving G. So we've got negative log of our approximating density G applied to our data. So that's nice. You can show that mathematically. They have the same minimizer. Unfortunately, it's still not quite enough, because we still can't compute the cross entropy risk, because we're taking an expectation with respect to the data. The data was generated with PDF F. We don't know F. So we have to make an approximation, and we can show that the minimizer of the cross entropy risk is approximately equal to the minimizer of the cross entropy training loss. Right, so that's this third formula here. And the cross entropy training loss is just the negative log of G, where we plug in our observed training data. So we've got the tau here, right? And this G term, we call that the likelihood. So the cross entropy training loss is just the negative log likelihood. And if you've done statistics before, you might recognize this minimizing the negative log likelihood is the same as just classic maximum likelihood estimation. Okay, so essentially unsupervised learning boils down to maximum likelihood estimation. And here's where we're able to enforce this dependency structure in our time series data. So we can decompose this likelihood term as a product of these conditional densities here. So just using the product rule for probability density functions. We get the product of the conditional density of the current observation YT given some of the previous observations in the time series. We'll just take the previous R observations in the time series. Okay, so that's just something we can do. This will this will allow us to capture rather the dependency structure in our time series data. If we're able to do that, if we're able to solve this minimization problem, we'll call the minimizer theta hat. Okay, and that's essentially the training process. That's what that's what training is in machine learning. That's what we call learning. It's just solving an optimization problem. So if you're not so much into the equations and formulas, then you can think of training like this. So if we have some time series data in black, it means that before we've trained our model might think that the data lies on this. So before we train, our model thinks that our data lies on this red line here. But of course, we have a probabilistic model, so we're allowing for some uncertainty in our data. So we've got this red shaded region around that red line. And then after training, after we've fit the model to our data, we've got a much better idea of what the data looks like. So our model now thinks that our data is on this new red line, very close to the observed data. But of course, we still allow for a bit of uncertainty and natural variation in our data as well. So this data in particular comes from Dogecoin, the cryptocurrency. Okay, once we've done training, we fit our model to our data, we want to use that model to make a forecast into the future. So once we've done the training, we've solved our optimization problem, learning's done, we've got our theta hat, we plug that into our model. We want to use our model to generate a point forecast into the future. Okay, so we make a guess as to what's going to happen in the future based on what's happened in the past. Another benefit we get from using these probabilistic models is that we can actually represent our uncertainty in our forecast as well. So we can make a guess as to what's going to happen in the future, but we're not going to be certain that that's going to be right. So we can also give a prediction interval or an interval forecast to just sort of let whoever is interested to know, we think this is going to happen, but we're not sure. It could be anywhere between these two bounds. Okay, so we give a point forecast and prediction interval. Now, we can make a forecast, we can make a guess as to what's going to happen in the future. And once we've actually waited and seen what's actually ended up happening, then we're able to see how good our forecast ended up being. Right? So if we just wait a few time steps, so here we were predicting into the future h steps, so we've got y and plus 1 to y and plus h. Got these hats on top of these y's to denote that they're approximations given by our forecast. We actually wait and see what ended up happening. So we've got these true y's into the future. Then we can compare how good our forecast was versus what actually happened. So one way of comparing how close the forecast was to what really happened is by using formulas such as the mean absolute scaled error. Mean absolute scaled error, if you just ignore the denominator, then it's just the mean absolute error, very common way of measuring the discrepancies between two sets of data. And we do this scaling on the bottom, which allows us to remove the effect of scale in the data. And if we want to try our model on lots of different types of data sets, we will have a fair comparison to see how well it does on one data set compared to another data set. So we use these scaled functions and measures. There's a formula for testing how good our prediction intervals were as well. So we want good point forecast and we want good prediction intervals. We can actually see how good our prediction intervals were. An example of a way of doing that is using the scaled pinball loss. So yeah, the formula, don't get too hung up on what it looks like in maths. The idea is that the smaller the pinball loss, the better our prediction interval was. And we also scale it again to be able to compare fairly across many different data sets, because we want a model that works well for all types of different data. So again, if you're not so big into the math and equations, that's okay. You can think about what these measures of accuracy do like this. So here is an example of a bad point forecast, right? We have our training data in black. That's what we train our model on. What ended up happening is in red, right? And our forecast that we gave is in blue. If that was our forecast, you know, that's a bad forecast, right? We didn't at all come close to what actually ended up happening. Okay, something like this. So here our point forecast wasn't perfect, but it certainly was much better than that previous forecast. So something like this we would call a good point forecast, or at least it's a better forecast than before. Okay, so the mean absolute scaled error will give us that information. Now, for prediction intervals, there's also examples of good and bad prediction intervals. So I would say that this is an example of a bad prediction interval, and that's because it's very wide, right? So it's too wide, it's not very informative. Anyone could just say, oh, you know, I think anything between here and here could happen, and you just give a huge range, right? That's not very useful, right? Anyone can do that. This is a bad prediction interval. On the flip side, we also don't want to give prediction intervals that are too narrow, right? Because if we're too narrow, we could end up missing what really ends up happening with the data. So we don't want to give prediction intervals that are too wide and non-informative. We don't want to be too overconfident in our predictions by giving a really narrow prediction interval. You know, we don't end up capturing what happens at all. Somewhere in the middle is what we would classify as being a good prediction interval. All right, so something not too wide, not too narrow. We capture at least most of what ended up happening in the future. So you can see a little bit of the test data escaped our prediction interval here, but we did get the majority of it. Something like this is what we're after, and the scaled pinball loss will be able to tell us this. Okay, so that's essentially machine learning for time series in a nutshell: training and testing, making a forecast. Now, introducing neural networks into our machine learning models. So a neural network sort of looks like this. This is an example of a neural network. This neural network actually represents a multi-layer perceptron. Okay, so we have our input layer on the left. We take as input some of the observations in the time series. We feed it through to the first hidden layer of the neural network, feed that hidden layer into another hidden layer, and then feed that hidden layer to the output layer. Okay, so mathematically, what's happening here is that we take as input a vector of data, y, and then we feed that into the first hidden layer. Right, so what that means is that we just apply a linear transformation. So we apply a linear transformation to that input with a weight matrix W and a bias vector B, and then to that linear transformation, we apply some simple nonlinear activation function, call it S. So overall, we have a nonlinear transformation. Feed that into the next layer, the different linear transformation, apply an activation function again, and then feed that into the output layer. So in the output layer, in this particular case, we have a one-dimensional output. So our weight matrix is actually going to be a vector, and our bias vector B is actually going to just be a scalar for this one-dimensional output. Okay, so these neural networks are great. There's one particular theoretical reason why neural networks are so popular and why they work so well. It turns out that if you are given any function, then there exists a neural network that can approximate that function arbitrarily well. Right? So we call that the universal approximator property of neural networks. It holds for multi-layer perceptrons amongst other types of neural networks. So yeah, essentially there exists a neural network for everything, right? You can do anything with a neural network as long as you do it well. So it's not a one thing to rule all, but in theory, you can do anything with neural networks, which is kind of nice. Okay, so how do we use neural networks for time series data? Remember, to train a model on time series data, we want to solve this optimization problem where we want to minimize the negative log likelihood. and our likelihood is just the product of these conditional densities of the current observation given the previous observations in the time series. So in order to train a model, we just need to be able to specify a likelihood essentially. And to specify a likelihood, all we need to be able to do is be able to specify the forms of these conditional densities or these conditional distributions. One rather simple way of defining a conditional distribution using a neural network is as follows. We can just say that the current observation yt, given some of the previous observations in the time series, just comes from a normal distribution with mean mu t and variance 1 or standard deviation 1. Right, so our data just comes from a normal distribution with some mean, and we'll say that the mean is modeled by the output of a neural network, and this neural network takes as input a vector of the previous observations in the time series. Right, so we get the previous observations in the time series, to put them into a vector, plug that into a neural network, and this neural network is going to have weight and bias parameters collected into this vector theta. This vector theta is essentially going to be the parameters of our model that we want to fit. Okay, so yeah, this is one basic way of defining a model for time series data using a neural network. The neural network can be any type of neural network really. A common way of doing it is to just use a multi-layer perceptron, but things like recurrent neural networks and convolutional neural networks, they're able to work perfectly fine as well. So to train this model, remember we want to minimize the negative log likelihood. You can actually show that with this model using the normal distribution, that this objective function turns into this least squares problem here. So you can show that minimizing negative log likelihood is the same as minimizing the average squared deviation between our observations y and what our neural network predicts that observation to be. Right? We just take the square of that deviation. Right. So it's just a least squares problem. If you've done machine learning before, you've probably seen the least squares problem pop up quite often. It's a very common way of fitting models. And if we're able to solve this optimization problem, which we are, then we can make a forecast using this model by just using the neural network to give us our point forecast, right? So just use the network, plug in the previous data, and just predict out into the future. And we can give prediction intervals by using properties of the normal distribution. We just give a prediction interval as being equal to our prediction, or the mean, plus or minus this Z score. So from the normal distribution, just use properties of that. If we want to give a P% prediction interval, so P is like our level of confidence in our prediction interval, then we just take the 1 minus P on 2 quantile from the standard normal distribution. Okay, so this is just a relatively simple model for time series data based on neural nets. This model's great because it's simple, but with the simplicity comes some limitations. So with time series data, it's actually quite common to get data that has heavy tails, right? So there's a lot of variation in the data. The time series data can change very rapidly in a short amount of time. We can see skewness in our data. Okay, so with the use of the normal distribution is symmetric. So say on both sides. That certainly may not be the case with a lot of time series data. And we also can see heteroscedasticity. This is actually very common. So with the normal model from before, we had a variance of 1 or a standard deviation of 1. But that amount of variation in the data may actually change over time, right? So that's very common in financial data, for example. The value of a certain financial product, for example, a stock, could be very volatile at some point in time, and then the volatility might go down for another period of time as well. So we want to be able to handle that with our models as well. So yeah, the result is that the simple neural network model may not be good enough in a lot of applications of interest. So yeah, visually, some of these data sets might look like this. I'd say this data is an example of data with heavy tails, right? So we have a lot of variation. The value or the observations sort of vary a lot in a short amount of time. And these data sets over here have a bit of skewness and a bit of heteroscedasticity as well. So you can see, for example, in this data set on the right, in this little section here, this data has actually got a bit of right skewness, right? So it's skewed up. So most of the data is sort of lying around 0 or near the bottom of the graph, but it's actually fluctuating up a bit, but still staying mostly grounded at 0. So that's an example of skewness in time series data. And obviously we've got the heteroscedasticity, where the amount of variation in the data changes over time. So we've got a period of very low amount of variation, then it gets really volatile, lots of variation, then dies back down a bit. So we want to be able to handle data sets like these, as well as the nice data sets that aren't so nasty with these properties. So one way of dealing with these issues is to beef up the type of distribution that we use. Okay, so before we were using a normal distribution, where we were just modeling the mean with a neural network, and we had the variance of 1. We could instead replace that normal distribution with some type of skewed distribution, where we parameterize the distribution using a location parameter, a scale parameter, and a skewness parameter. Okay, and we're going to model each of these parameters using neural networks. Okay, so we'll model each of these parameters as being the output of a neural network. These will be separate neural networks with their own sets of weight and bias parameters, theta 1, theta 2, theta 3. And this allows us to capture the changing location of the data. So what happens to the data on average, the scale, that's the variation in the data, that's allowed to change over time, and also the skewness in the data. We can handle varying amounts of skewness in our data too. So that's really good. An example of a skewed distribution, a simple example is just a skew normal distribution. If we choose to use the skew normal distribution, then that means that the form of the conditional density G, the current observation given the previous observations, just has this form here, 2 times the PDF of the normal distribution, times by the CDF of the normal distribution, evaluated at delta times y, where delta is the skewness parameter. There are other types of skewed distributions as well. So for example, skew Laplace distribution and the skew T distributions, they're very common. And really which one you want to use will depend a lot on how heavy the tails are in your data, how much variation you see. We'll actually learn how to choose the distribution automatically in a model selection part. Okay, so we've got this new model. It's quite a bit more sophisticated than before. We've got 3 different neural networks. We've got a more complicated distribution. We still want to be able to train such a model so we can actually use it. So to train a model, remember, same principle applies. We want to minimize the negative log likelihood. Now, if, for example, we want to use the skew normal distribution, then the form of this conditional density is going to look like this. And plugging in for what the PDF and CDF of the normal distribution are, we get an objective function that looks like this. All right, we want to minimize the negative log likelihood as a function of our model parameters. So we just essentially want to tune these weight and bias parameters of our neural networks. So it's going to be 3 neural networks in the definition of this objective function. There's an integral, it's quite nasty, really. So if it looks quite full on, that's because it is really, but it's still manageable. Okay, so great thing about having a computer is that we can essentially just plug this straight into Python. So I use PyTorch for my deep learning, but TensorFlow is another really popular option for doing deep learning. As long as you can actually physically code your objective function into Python, and in particular using PyTorch objects or objects from TensorFlow if you prefer that, then that's all you really need to be able to do, because you can run gradient-based optimization methods and actually try and solve this optimization problem, as long as you can actually write this out. And in this case, we certainly can. So PyTorch is really nice, and other deep learning libraries are really nice because there's automatic differentiation. We don't have to compute the derivatives of this function by hand. It'll do it for us. And gradient-based optimization methods such as stochastic gradient descent, ADAM, ADA delta, SGD with momentum, all those nice optimization methods, they're all implemented for us. And we can use gradient-based optimization to try and solve this problem. So super nice, super cool, extremely useful for testing out sophisticated models. So while this is all well and good, there is one caveat to that. Okay, so if we can plug this objective function in, we can run gradient-based optimization to try and optimize it. But the problem is that such a sophisticated objective function with 3 neural networks in its definition, we would expect the objective function to be very multimodal. Okay, so what I mean by that is if we were to project our loss surface or our objective function down to 2 dimensions, to 2-dimensional input, we might expect the loss function to look a bit like this. Okay, so there's lots of peaks, lots of troughs. And if we were to run gradient-based optimization, what would happen is we would start at a point on the surface, and we would essentially follow the gradient down and get stuck in a local minimum. All right, so we would get stuck down in some local minimum. Right, and if we started the optimization from a different point, we would get stuck in a different local minimum. Right, so if we run optimization a bunch of different times, start with a bunch of different starting points, we would end up in a bunch of different endpoints. And essentially all of those local minima that we could get stuck in are going to correspond to different models, right? So do optimization a bunch of times, get stuck in a bunch of different minima. They're going to correspond to models that essentially they've all been trained on the same data. So they're all going to agree on what the training data looks like. But because they're in different regions, we would expect them to have different opinions about what happens in the future. Right? So if we use each of those models to make a forecast into the future, they're probably going to give us different forecasts. But that's actually a good thing because we can combine them all into one big powerful forecast. Right? So that's called making an ensemble. We get a bunch of different models and combine them into one big model. So we're not just relying on one single model to give us our forecast, because we might have got stuck in the wrong local minima if we just use one model. We want to take care of that. So assuming we know how to make a forecast with this model, these models, then if we use the ensemble to give us a forecast, we would get a bunch of different forecasts from each different model, so a bunch of different point forecasts, right? A lot of the models tend to agree on what might happen in the future, but there is this one particular model, for example, here, that thinks that the data is going to shoot up really high, but most models think the data will sit around here in the future. So we get a bunch of different point forecasts. We can just take the average, for example, to be the complete ensemble forecast, but there's other ways of combining these different forecasts into a single one. They all have their upsides and downsides. And with these varying point forecasts, it's going to correspond to prediction intervals that look a bit like this, right? So the prediction intervals are going to get wider the further in the future we forecast, right? So, different models are going to shoot off. So prediction intervals are going to get wide, but that's actually really good and what we'd expect, because as we try and predict further out to the future, we're going to get less and less certain that our forecast is actually going to be correct. Right, so we would expect to see an increase in uncertainty as we go further out to the future. And that's exactly what using ensembles for forecasts is going to give us. Okay, so that's something really nice. The details on how to actually use the ensemble to make the forecast, it's I guess a bit nitty gritty, but I'm happy to explain it more at the end if you're curious. For now, let's assume that we can do this and it's really good and really nice. Now, if you've done machine learning before, you've probably encountered model selection. So model selection is extremely important for a number of reasons. One reason, which you've probably seen before, is that There's usually a lot of design choices we make in designing a model. So lots of different hyperparameters, combinations of models. We want to essentially get the best model out of a bunch that we're considering to make the best forecast, the best predictions, right? So normally we would try a bunch of different models, train them all on the same training data, make our predictions, see which one made the best prediction on the test data, and we would use that. Okay, so that's like doing model selection. But I think model selection is also really good for another reason, and it's because of this. Imagine that you've got someone, say a researcher, and they don't specialize in any sort of data analysis. Maybe they do like science, say, right? And they want to do a study, they want to investigate some phenomenon, and they do their study, they collect their data, and they want to use their data to get their results, right? They want to make a prediction, they want to make a forecast, what they think is going to happen in the future. They want to use the best model possible, but they don't have a very deep understanding of all these sophisticated models, right? So, the state of the art, essentially. They want to use the state of the art model, but they don't really understand how to use it. If we have a model selection procedure in place, they don't need to understand it. They can go, oh, I want to use your model. You go, okay, here it is. We'll do all the hard work. We'll do model selection. We'll design the best model for your data, and it'll give you the best quality prediction. So I think that's another really good reason why we should do model selection. Model selection essentially goes like this. We hold out some validation data from our training set to do model selection with, right? So at training time, we don't have any test data. So what we do is we actually sacrifice the last bit of our data and keep that as like a mini test set, right? We call it a validation set. And we train on the reduced size training set. And we use that leftover validation data to try and test our model. Right? So we train on the training data, test on the validation data, and the model that gives us the best predictions on the validation set, we're going to use that as our final model. So we treat the predictive performance on our validation data as a function that depends on the sort of the characteristics of the model or the hyperparameters of the model. We collect them into this vector here, so var theta. Some of the things that we're able to choose with this model selection procedure include the form of the conditional density that we want to use. Right? So remember before I mentioned that we can use a skew normal distribution, a skew Laplace distribution, or a skew T distribution, right? Depending on which distribution is best for which type of data. We obviously need to design a neural network, right? So that's a huge problem in deep learning. We need to get a good neural network. We need to choose the width of the neural network and the depth of the neural network that's suitable for the data. And in time series specifically, we need to choose the lag, right? So we need to decide how far into the past do we need to look in order to make our forecast, right? Do we just need to look one step back, or do we need to look back maybe 100 or even 1,000 time steps back in order to get an accurate prediction? So these are some of the things we need to decide, and we can fine tune them using model selection. Okay, now Bayesian optimization for model selection. So Bayesian optimization it's relatively new. It has been around for a long time, and the idea is that it's based on it being around for a very long time, but it's only being used for model selection and machine learning relatively recently. And I think it's a really cool idea, so that's why I wanted to use it as part of my project. So Bayesian optimization, just generally, it's a global optimization method, and it's particularly well suited for certain situations. So the idea of Bayesian optimization is it just gives us a method for optimizing some objective function, and it tries to find the global optimum. All right, so in this case, we'll do a minimization problem. We want to find the smallest error in our predictive performance, right? So Bayesian optimization is particularly well suited when our objective function we're trying to optimize behaves like a black box, right? I'll get to, good question. I'll get to that at the end. I'm very happy to talk about different libraries in Python. With Bayesian optimization, if our objective function trying to optimize behaves like a black box, so a black box function is one where we can give it an input and it'll give us an output, and that's it. Right? We're not able to take derivatives to do gradient-based optimization. not able to get curvature information about our function, all we can do is give it inputs and it'll give us outputs. So that's exactly like the situation we have when we're doing model selection. We have some collection of models, right, with different characteristics. We choose one set of characteristics for a model. We train that model and we test it on our validation data, and we see what performance it had at predicting the validation data. Okay, so that is like a black box function. So that's good for us. One reason to use Bayesian optimization. Another is if our objective function is really expensive to evaluate, right? And the evaluations are noisy, right? So an expensive objective function can mean a lot of things. So one way that an objective function can be expensive to evaluate is if it's expensive in terms of time, right? So that's particularly useful for us. So if our objective function is such that we give it an input and we have to wait a long time before it'll process our output, Bayesian optimization is great for that. So in our particular case, it takes ages to test a model, right? Because we're trying to test these ensembles of models that have neural networks in them. You know, each particular model is going to have 3 neural networks in it. We've got an ensemble of those models. It takes a long time to train and do the testing before we get our result to see how good the combination was. Models can also be expensive to evaluate. Objective functions can be expensive to evaluate in terms of money as well. It can actually cost a lot of money to evaluate objective functions. In our particular example, you might be training your models using, for example, cloud computing. Right? You might be hiring out some hardware, maybe hiring out some GPUs on the cloud or TPUs, and it actually costs you money to use them. So you want to minimize the amount of use you have. So Bayesian optimization, it's relatively computationally intensive compared to other optimization methods, but it works really well when done right. So it's particularly well suited for these types of situations, which is exactly the one we're in. Now, some details. So Bayesian optimization is always going to be paired with some sort of, we call it the surrogate model or regression process. So usually you'll see Bayesian optimization paired with Gaussian process regression. So Gaussian process regression or GPs, super interesting idea all on its own. You can use them to do regression, and they're good because not only do they tell you what they think is going to happen, but they give you uncertainty in your predictions as well. They're really nice, really cool. I encourage you to look into them if you're interested in machine learning. So to do Bayesian optimization, model selection with Gaussian processes, what we do is we first test a few different hyperparameters of the model and record how well they do with their predictions on the validation data. Right? So we test a bunch of different models first, see how they all go, see how the different characteristics of the model go with predictions. Then that'll give us a bunch of inputs and a bunch of outputs. Right? So the inputs will be the characteristics of the model or the hyperparameters, and the outputs will be all their predictive performances on the validation data. So the inputs and outputs, we fit a Gaussian process regression model to these inputs and outputs, right? And that'll help us to guess the performance of other models that we haven't tested yet. Right? So if we make a model of how good our original models were, then we can make an informed decision about essentially what hyperparameters should work and what hyperparameters might not work. So you've got a model for how good these hyperparameters are. We then use what's called an acquisition function to decide which combination of hyperparameters we should try next. Okay, so there are reasons why we wouldn't just go for the model that looks like it'll be the best for making predictions, because usually there's a budget associated with Bayesian optimization. So we want to go to the most promising model. That could be in terms of it should have a good predictive performance, but we also want to try models that don't take long to train, maybe, or they're cheap to train, don't take long. So they train efficiently. And also simpler models often do outperform more sophisticated models anyway. So we want to try and find simple models that make very good predictions. An example of an acquisition function is the expected improvement. acquisition or expected improvement per second, which is the one that I tend to use. So it takes into account the performance of the model and how efficient the model is. Okay, so we use an acquisition, tells us what to try next. We go out and try it, see how well it does. We get a new data point, we update our Gaussian process model, and we repeat, right? And we repeat until we stop, right? So we can stop when we've run out of time allocated. We can stop when we're happy with our results. We can stop when we run out of money. We can stop when we have done a certain number of iterations. There's a lot of different criteria you can use. Okay. This is just a simple little illustration of how Bayesian optimization works, because it puts out some pretty nice pictures, especially with the Gaussian process regression. So imagine that we're only trying to tune one hyperparameter, right? So our vector of hyperparameters is just a scalar. You can take values 0 to 1. And we want to use Bayesian optimization to tune this hyperparameter. Suppose that so the hyperparameter input, the output is going to be the predictive performance of the model given that hyperparameter. Suppose that there's some true sort of underlying predictive performance for all of these hyperparameters given by this thin black line. But of course, in our training procedure, we use stochastic methods for training. Often we need to make approximations when we make a forecast. So there's a lot of input of uncertainty. We can't make exact evaluations of this objective function. So for example, here we've got a black dot. It's an observation from our function, but it's a little bit off from the function. All right, so Bayesian optimization handles that really well. That's okay. So after this first observation, a Gaussian process thinks that the objective function looks like this red line, right? But really it's a black line. And also with Gaussian process regression, we get this measure of uncertainty in our prediction as well, right? So near the observation, the uncertainty is decreased, and away from the observation, we're very uncertain about what happens, which makes sense. Down the bottom, we have our acquisition function. So this tells us what's a good choice to try next, right? Which hyperparameter should we try next to try and minimize this, this error. Right, so minimize this optimization objective function. So it's saying that a low expected improvement for regions where we've already tried, we should go away from the middle, try something away from there. So I think what we do is maximize the acquisition. I think the maximum is to the left. Yep. So we try that data point next. We plug in hyperparameter, get our observation. So we have 2 data points now. We fit a Gaussian process to those 2 data points. We update our red line. We also update our uncertainty, and our acquisition function changes as well. So now it's saying, right, a low expected improvement near where we have data. You're much better off still trying away from where we have data, right? So maximum is over here. We try over there. New Gaussian process, new data point, new acquisition. And we just repeat this for as long as we like, or for as long as we can. So after, I think this is 10 iterations with this example, what we see is that Bayesian optimization told us to keep trying around this region here. And obviously this region is where the true minimum of the function is. So that's kind of nice. It kept directing us to here. And we can see that if we were to keep going, the acquisition function tells us to keep evaluating in this exact region here. So it is honing in on the true global minimum of the function. So obviously this works just fine in higher dimensions as well. If we're trying to tune multiple hyperparameters at once, that's fine. Gaussian processes fit to multi-dimensional inputs very easily, and we can tune multiple hyperparameters all at once. So yeah, I thought the pictures are just kind of nice. Gaussian processes make nice pictures. So yeah, hopefully that explains Bayesian optimization a bit too. Okay, so the model. So when I say the model now, I mean the actual neural networks, the distribution, and the model selection procedure all in one. There's code implementing this. So there's a module. It's available on my GitHub. I'll have the link up at the end. Very simple to use. That was one of the goals of my project. So we just import a bunch of packages in Python, some standard ones, get some data. All right, so here I've just got some Tesla stock price data from the Y Finance module. Down here, we have our train test split. Right, so we split the data into training set and test set. And down the bottom, that's the actual using the model, right? So we just initialize the model. We do model.fit on the training data. We do model.predict. That'll give us a point forecast and our prediction intervals. And we do model.plot, and that'll give us this plot down here. All right, so we output a plot like this. We've got our training data in black. We've got the test data in red, so what actually ended up happening, and what our ensemble forecasted. Okay, so this is just the most basic way to use a model without doing any sort of tuning. There's a lot of extra things you can add in here to make it better. In its basic form, it was able to predict this. So we can see the predictions were pretty good at the start, but they gradually shifted away. The model thought Tesla stock price was going to increase, but it actually ended up decreasing a bit. That's okay, because we've got a bunch of different prediction intervals here. We've got 50% prediction interval all the way up to 99% prediction interval. And these prediction intervals did actually capture what ended up happening. So it wasn't too much of a shock to the model to see that change. Some other results. I tried it on Dogecoin data, so training data in black, test data in red, so what actually ended up happening, and our ensemble prediction in blue. So yeah, the blue line, relatively close to the red line, right? We didn't do too bad at forecasting that. You see all these other pink lines as well. That's just point forecast from individual models in the ensemble. So they were all doing all sorts of different things, but on average, they did really well. And we can also see that the prediction intervals get very wide very quickly, which just means that, the model, further out we try and predict into the future, the model just gets very uncertain very quickly, which sort of makes sense because cryptocurrency is very volatile, it's very hard to predict. Flow of the Nile River data, a very popular or very commonly used data set in time series analysis, measuring the flow of the Nile River. Again, our model did okay at predicting, and we can see that the prediction intervals did capture the test data, even if our point forecast wasn't spot on. So that's sort of nice. Some extra data here. This data was actually simulated from the model itself because I wanted to really push it to the extremes, generate some really nasty looking data, really heavy tails, these crazy outliers. Well, not outliers, it's just due to having heavy tails. And wanted to see how well it did versus some off-the-shelf forecasting methods. So on the left, we've got some pretty nasty looking data. We fit our model or fit the model to it. We've got our point forecast and our prediction intervals. And on the right, we've just compared it against ARMA. So some of you might have come across ARMA before. It's just an off-the-shelf forecasting method. In Python, the ARMA implementation doesn't actually give prediction intervals. Well, at least the version I was using from the stats models library. So we just got a point forecast, and we can see the point forecast from ARMA in blue. It was okay, but it was sort of a bit inconsistent. Whereas our this model with neural networks, it was able to identify that there was skewness in the data, so it skewed downwards, and it was able to pick that up. And we've got prediction intervals capturing all the test data, which is pretty nice. So that's all I wanted to talk about. So thanks, everybody. If you're interested in looking at the code, there's a GitHub available. Feel free to check that out at your leisure. So thanks, everybody. Happy to take some questions. I'll open up the chat. Any particular reason you picked PyTorch over TensorFlow? Yeah, so that's a good question. There's a big debate about which is better. I think at the time when I started deep learning, PyTorch was a little bit more user-friendly. There was a little bit sort of TensorFlow was great, and a lot of people were using it, but it's just a little bit simpler with the syntax and that for using PyTorch. And my supervisor had some resources done in PyTorch as well, so I just picked PyTorch. I think nowadays the user friendliness between PyTorch and TensorFlow is sort of, the gaps is closed up a bit. I think TensorFlow's, I haven't personally used it much, but I think as far as sounds of it, it's pretty easy. So either or, you can pick one over the other, and you're not really going to be getting any downsides to picking one. I just started using PyTorch, and I think it's great. It's great for doing research and deep learning, getting very sophisticated models and training them and testing them. But yeah, Keras is also another one. So that's a skin, a wrapper for TensorFlow. Makes it nice and easy to do deep learning. Any recommended books on Gaussian processes? Oh yeah, so there's probably the first book you should try and read is Gaussian Processes for Machine Learning by, I can't remember the author, but if you just Google Gaussian Processes for Machine Learning, it'll be one of the first results. And yeah, it's an excellent book. It's very good. It's like the Bible on Gaussian processes, just about. And once you've done sort of reading that, it gets a bit sophisticated quite quickly. There's lots of other places to talk about GPs. Of course, you can read my thesis. There's a bit of details of GPs in there. Yeah, lots of different places have GPs. I'd start with Gaussian processes for machine learning. Any resources you recommend to learn time series forecasting? Okay, great question. So I think I had a little bit of an unorthodox introduction to time series forecasting. There are some statistics and economics courses that may teach it at uni. Rob Heinemann, he's a researcher. I think he's based in Melbourne at the moment. He specializes in the analysis of time series data. Try and look up some of his books. He's written a few. He's a very good author, really knows his stuff. I'd recommend checking out some of the books that Rob Heinemann has written for getting started with time series forecasting. GP for machine learning, Carl Edward Rasmussen, Chris Williams. Yeah, yeah, that looks familiar. Good. There's heaps of stuff with GPs too. Like that book's just the start of it. There's all these extensions that people have done. People have dedicated all their research to GPs, and they've shown that you can basically do any machine learning task with Gaussian processes. You can even make deep Gaussian processes and all this sort of crazy stuff. It's a really interesting area. Okay, next. Is there any performance difference when training models on raw Y values versus delta Y? What's the difference in training models on raw Y values versus delta Y? So what do you mean by delta Y when comparing the performance versus raw data? This particular model that I've implemented just takes in raw data as its input. Especially with the neural networks. The neural networks usually don't need any pre-processing of the data to be able to handle it. Change in Y values. Oh yeah, so a lot of people do deal with the differenced series. So I think that's more from a modeling perspective. I'm not sure. It can be more computationally efficient to work with difference data, but that's mostly because the models you fit to the difference data are usually simpler. So one reason why you would do differencing in your data and consider your delta Y's is because you want to remove the non-stationarities in your time series data, right? So you can fit a model to your data that assumes, you can fit a model to the difference data that assumes it's stationary. So simpler models, more efficient to fit. Yeah, but there's a lot of models that can handle, pretty wild data, non-stationary, all that sort of stuff. The performance really depends on the model, how efficiently it's implemented. If you implement it yourself, or I know if I implement models myself, it's often a lot less efficient than if you use an off-the-shelf package from Python, for example. Yes, I don't know, hopefully that sort of gives you a bit of insight into that. So I know the ARMA model that I compared against before, there's an ARIMA model as an extension, and ARIMA considers fitting an ARMA model to the different values in the data, so it can handle non-stationary time series. My model, or this model with the neural networks, it seems to do okay with non-stationary data, although it's actually not theoretically, it's not a difficult extension to actually deal with non-stationarity in this model too. If you also give your neural networks an input of time t, then it can learn how the distribution changes over time. And that's exactly what non-stationary data is, the conditional distribution changing over time. What is your background, i.e. computer science, mathematics? Yeah, good question. So I did a Bachelor of Mathematics, and then I did a Bachelor of Math Honours after that. So I majored in data analytics and operations research, partly because I like data analytics, but partly because it was actually a relatively easy major to get. Courses just happened to line up that way. I did honours, Bachelor of Math Honours, and obviously this was basically my project. So there's a lot of statistics, maths, machine learning, and deep learning sort of all packed into one. My background in computer science is essentially nil. It's one of the limitations of mine. It'd be nice if I was a bit better at programming and understood more about computer science. That's something I've picked up as I've gotten more into stats and especially deep learning as well. There's a huge computer science aspect to deep learning. So main background in math. What do you plan on doing after honours? Data science, I guess. So math and math, stats, machine learning, going into data science. There's I think data analyst is probably one of the most common jobs available. Machine learning engineer is another job. I think they're a little bit more scarce. They often want a lot of different credentials for them. You probably had me, well, I don't know, maybe I've seen some of you as being a tutor as well. I do quite a lot of tutoring. I really enjoy tutoring. Is there any other questions? All right, great. Yeah, cheers everyone, and enjoy the rest of your night.
Thanks so much for your time, Jonathan.
Yeah, thanks, mate.